Let us start today's lecture on soil dynamics. We are continuing with our module 4, that is dynamic soil properties. So, a quick recap what we have learned in the previous lecture. First, let us look at this page, that is any cyclic test in the laboratory. We can get the data for cyclic shear stress versus shear strain. So, the plot of shear stress versus shear strain will start from this point origin 0 0. It will go up in the loading curve. Then, if we release the load, because this is a cyclic load, this is unloading curve, and then again reloading curve. So, like that, these are the cycles. As per different cycles, we will get different envelope of this tau versus gamma plot. Now, from this we have identified that the slope of the curve is not a constant value, but it is changing, and we have learned that if we draw a tangent at the initial portion of the curve, that is called G max. G is nothing but the shear modulus, which is given by this tau by gamma, shear stress by shear strain is shear modulus. So, the initial tangent modulus is nothing but maximum shear modulus, the slope of the curve at this point. Now, if we take slope of the curve at any point with any other cyclic shear strain value, say gamma 1, so we can draw a tangent at that point, and the slope of the curve, whatever it will give us, the value of G is called tangent shear modulus. And another shear modulus we have seen, which is if we join this point to the origin, the slope of that line will give us another shear modulus, which is called secant shear modulus. And what are the application of these three different types of shear modulus, that also we have seen in the dynamic analysis. We can subclassify any dynamic analysis into three categories: linear analysis, equivalent linear analysis, and nonlinear analysis, based on what is our input value of the shear modulus we are using for the analysis. When we are using the maximum shear modulus, it is linear analysis, which we have seen that it is the most easiest or simplest analysis, because here the value of G max remains constant throughout the analysis, and easily we can estimate this through any field test also, because G max is correlated with the shear wave velocity of the material through the equation rho V s square. Whereas, most complex analysis, but most accurate analysis is nonlinear analysis, where we are able to capture the behavior of the soil material, that is shear modulus of the soil material at any value of its cyclic shear strain. So, we should use at that point G tangent shear modulus. The tangent shear modulus, as it is keep on changing with change of the curvature of the tau versus gamma plot. So, in your entire analysis, this is a completely variable parameter throughout the analysis, which is nonlinear in nature. So, that is why this is most complex, but gives most accurate result. Now, depending on the accuracy required for a problem, we can compromise in between these two extreme cases, that is simplest analysis and the complex analysis. The in between one is called equivalent linear analysis, where we can use the secant shear modulus if we are aware of that up to a particular level of cyclic shear strain our soil model is going to subject it to, then in that case we can simply use the equivalent linear analysis by using secant shear modulus. So, coming to the slides, the stress strain behavior for any cyclically loaded soil, this is the equivalent linear model with G secant modulus, and from that we have seen what is called backbone curve. The plot of tau versus gamma is known as backbone curve, and if we represent it in a non-dimensional form of G by G max versus the log scale of this cyclic shear strain, and if we plot any data, the typical behavior for any kind of soil material will be something like this. It should start from 1, because at very low strain the value of G is nothing but G max. So, obviously, it should start from 1, and then with increase in cyclic shear strain, the tangent shear modulus decreases. So, that is why this G by G max ratio is less than 1, it keep on decreasing, which is known as modulus reduction curve. Then we have seen several empirical relations to compute the maximum shear modulus, and caution also I have mentioned in using the empirical relations. First of all, we have to be very careful in which unit they are proposed, because all empirical relations are unit biased. Another caution is that these empirical relations derived by several researchers, though mentioned for sand, it may be because of only the local regional soil. For a particular soil, it may be valid. For other region of soil, it is still questionable whether it will be valid or not. That needs to be checked. So, this is the equation proposed by Seed and Idris in 1970. Other relationship have been proposed by several other researchers also, depending on in situ test parameters, that is standard penetration test value or cone penetration test value, to compute the G max. Also, the dialectometer test value or pressure meter test value also, the G max can be computed, as was proposed by several other researchers for different types of soil. Now, some more estimation of G max value from cone penetration test result, as was proposed by Baldi et al. In 1989, that they have used not only normally consolidated soil, that is with OCR value 1, but also over consolidated soil with OCR value of 10. So, different values of OCR they have used, and then they have plotted in the y axis the variation of G max by QC, which is of course non-dimensional. So, when you are getting in literature this kind of non-dimensionalized results, they are much better than the equations which are involved with dimensions. And in the other x axis, it is QC by sigma v dash to the power 0.5. So, the typical variation for different OCR levels is like this. They have proposed for uncemented silica sand, these are the trends of the results, that is with increase in over consolidation ratio for a soil, the G max value will increase. That is what they have shown through the experimental results. Now, this is one important aspect. Let us see what are the effects of environmental loading conditions on this value of G max for both normally consolidated and moderately over consolidated soil. So, look at this table, what it says: if effective confining pressure, that is sigma m dash, if this value of effective confining pressure is increasing, what will happen to G max? That also increases, which is quite understood. Physically also we can understand this one, that as we keep on going much below from the ground surface, that is if we go deeper and deeper in a soil strata, if everything, all other parameters remain same, and soil obviously we are considering the homogeneous soil, then as we go deeper, the G max value will keep on increasing. So, that is what it is mentioned, effective confining pressure increases means G max value should increase. What happens if void ratio of soil is increasing? Then the G max value will decrease. This also we can understand physically. Void ratio increasing means what happens? That is, soils becoming more loose. More loose means strength of the soil will be much lower. So, that is why void ratio increases means G max value should decrease. Then let us look at another environmental factor, that is increase in geologic age. Geologic age means like formation of soil. If it is geologically very old ancient soil, or what we sometimes call the parent soil is present at any particular location, rather than a transported soil or filled up soil material from one place to another, if we do the test any of this cyclic triaxial or cyclic simple shear, what we will get the value of G max. With increase in geologic age, there will be increase in G max value, which also we can physically understand that older the soil, obviously the strength of the soil will be much more than the transported soil or filled up material. What happens if cementation of the soil changes? If cementation of the soil increases, cementation means obviously the bonding between the soil particles are much more. So, obviously, it is supposed to give higher strength. So, there will be increase in the value of the G max with cementation. What happens if over consolidation ratio increases? Just now we have seen, obviously, if over consolidation ratio increases, the G max value also will increase, because over consolidation ratio increases means earlier the soil was subjected to higher load. That is what means by over consolidated soil. Obviously, that will give a higher strength of the soil rather than a normally consolidated soil, which was not subjected to a higher magnitude of the load. Now, what happens if plasticity index increases? What is plasticity index? We know for fine grained soil, we know plasticity index, liquid limit minus plastic limit. So, if that value increases, the G max value increases with Pi only if it is a over consolidated soil, but if it is a normally consolidated soil, then plasticity index hardly is having much effect on the value of G max. That is what was found out by all these observations were made by Dobry and Vucetich in 1987. That is the source. Now, what happens if the strain rate, you know that all test, not only the dynamic test, also the static test, like if you take triaxial test or direct shear test, these are strain rate based. That is, if you change the rate of application of your strain, obviously, you will get different results or different modulus of the soil. Similarly, for the dynamic test also, if you keep changing the application of your strain rate, that is at which the rate of strain applied to the soil sample is changed, what happens to the G max value? It says almost no effect for non-plastic soil, that is mostly sandy type of soil or the cohesionless soil, but for plastic soil or for fine grained soil, it increases with increase in the strain rate. That is, if we increase the strain rate, then the G max value increases up to about 10% per log cycle with increase in the strain rate. And what happens if the number of loading cycles increases? What is meant by number of loading cycles? When we are doing the dynamic testing, as we have seen, we are doing loading, unloading, loading, unloading. So, that gives us the how many times or how many numbers of cycles of load we are applying to the sample. If we increase numbers of cycles of load to a particular sample, what will happen? The G max value will decrease with increase in number of cycles at large value of shear strain. But if you stop the experiment, then it recovers the G max value, whatever was lost due to the number of applied cycles of load, it will recover later with time in case of only clays. But with increase in number of cycles, the G max value increases for sandy soil. Okay? So, let us look at modulus reduction curve for fine grained soil. This is also proposed by Vucetich and Dobry in 1991. Modulus reduction curve means we know G by G max in the y axis and x axis is log scale of that cyclic shear strain which is applied to the sample. So, these are lab test results. Obviously, as we know the curve should start at this G by G max at 1 at very low strain level and then with increase in strain they will keep on decreasing. So, trend is known now to us. What happens? They observed for OCR value between 1 to 15, as the plasticity index increases for the soil, the variation will be like this. But remember, I am quoting here the observations by Vucetich and Dobry in 1991 through their lab test. Do not consider any of a particular test as universally truth. All these are open ended research problems. So, what I want to mention, look at this value of Pi. What does Pi 0 means? Pi 0 refers to it is a cohesionless soil, not a fine grained soil, right. So, that is why there is no plasticity index. But now, if we think logically, if you want to apply your mind logically, does it mean that for different types of sand, whether it is dense sand or medium sand or loose sand, the modulus reduction curve will remain same, a single line? No. Then what does it mean? It is meaning that G value or G max value, that ratio remains constant for irrespective of type of cohesionless soil, which is not correct. So, that is why this is a caution. Later on, by several researchers, this mistake was pointed out by researchers like Bray et al., that this is not the correct graph only for Pi equals to 0. So, whenever you are using this graph for your design or analysis, make sure that you are not using the line Pi equals to 0, but other graphs are correct. So, that is why limitation of any particular test etcetera must be known rather than using blindly these curves for analysis or design. Now, what are the effects of effective confining pressure and plasticity index on the modulus reduction behavior? So, this relation has been given, G by G max can be computed using this expression. K is a function which is function of the shear strain and plasticity index, and another function of this effective confining pressure to the power some factor of m, which is again a function of this shear strain and plasticity index minus m naught, where the expression for this function k, which is the function of gamma and pi, is given by this, and this coefficient, that is m, which is again a function of gamma and pi minus m naught, is expressed like this. And this n of pi, this function n of pi, you can look at here, for different values of pi values are listed with respect to these. So, these are the relationship obtained from the laboratory test results, which we have shown just now. From those curve, they have plotted and formulated a generalized equation to compute the value of G by G max at any strain level and for any particular value of plasticity index. And effect of mean confining pressure on modulus reduction curve, it is given by Ishibashi in 1992, mostly for Japanese soil. So, G by G max, earlier one was for mostly the California region soil. Okay. The Vucetich and Dobry's work is from California soil, they are from UCLA. And Ishibashi's work for Japanese soil, they also propose the effect of mean confining pressure, that is sigma m dash, if it increases, what we have learned just now, if sigma m dash increases, G max value will increase or strength will increase, right. So, strength should increase, that is why there is a shift of the modulus reduction curve in this direction as we are increasing the sigma m dash value for P I equals to 0 for different cyclic shear strain amplitude. And at high value of P I, they have shown almost there is no effect of mean confining pressure on the modulus reduction curve. So, when it is non-plastic soil, the effect is tremendous. When it is plastic soil, highly plastic soil, the effect is very marginal. Also, Vucetich and Dobry from their same results had proposed, this is actually the PhD thesis work of Professor Vucetich, who is a professor now at UCLA, Los Angeles, and he did PhD with Professor Dobry. So, another set of results they have proposed how the degradation of this modulus reduction curve occurs at different numbers of loading cycles. So, these n denotes the different cycles, number of loading cycles, and this P I denotes, already we have seen, for different plasticity index with a constant OCR of 1. And as I have already said, P I 0 later on has been proved by several researchers of UC Berkeley that these are not correct or should not be used. So, with this concept of effect of cyclic degradation of modulus reduction curve and how to estimate the different shear modulus and to apply them in the dynamic analysis, we have seen. In the next lecture, we will continue our discussion with the damping ratio, that is another important dynamic soil property. Now, coming to the next important parameter dynamic soil properties is damping ratio. So, the most important dynamic soil properties are a G value, shear modulus and damping ratio. Now, coming to the damping ratio, how to estimate the value of damping ratio? Let us look at this picture once again. From any cyclic load test, we are getting a typical curve like this, which is known as hysteresis curve. This tau versus gamma plot for different number of cycles of loading. Now, among these curves, the third cycle is called the representative cycle. Third cycle of the hysteresis curve is called a representative cycle to compute the value of damping ratio. So, now let me plot the hysteresis curve for a typical third cycle. Let us say the hysteresis curve looks like this. This is for third cycle I am using. So, let me give the nomenclature of various points, because it will be required for us to compute the damping ratio of the system. Let us say this is the origin, this point is say A, this is B, this is A dash, this one is B dash. So, damping ratio if we express is by eta, that is given by 1 by 2 pi times area of this hysteresis loop, that is area of A dash A. So, area of A dash A, that hysteresis loop, divided by area of triangle OAB and OA dash B dash. So, this is the expression to compute the damping ratio for any soil from the cyclic load test. How to obtain the G value that we have seen? This is the way we compute the damping ratio for representative cycle, which is mostly taken as the third cycle of loading. 1 by 2 pi area of this loop divided by area of this triangle and area of this triangle. Okay. Now, let us see what are the different effects of variation of this damping ratio with change of cyclic shear strain as proposed by various researchers. So, again the work of Vucetich and Dobry in 1991 for fine grained soil has been reported here. For different values of cyclic shear strain, how the damping ratio behaves, it is represented in percent, and for various soil they have considered with OCR value between 1 to 8, and for different values of plasticity index they have plotted the curve. So, as you can see, if the cyclic shear strain applied on a soil sample increases, the damping ratio of the material also increases. Also, if the plasticity of the soil decreases, then the damping ratio increases for the case of fine grained soil. Once again, the caution, that is later on several researchers has proved that do not use this curve for pi equals to 1, because it is not actually the representative curve for non-plastic soil, because for sand also we can have a set of curves depending on their relative density. It is not that it will be a single curve for all types of sand, but for non-zero values of pi the trend will be like this. So, it is better to observe the trend, that is with increase or decrease with pi, what is the effect on damping ratio, as well as on the change of cyclic shear strain, what is the effect on damping ratio. And the expression to compute the damping ratio value is proposed by Ishibashi and Zhang in 1993 for fine grained soil. They again used mostly the soil from the Japan region. So, this is the symbol for damping ratio they have used, is given by this expression. It is dependent on the value of G by G max and the plasticity index. So, that is why when you are taking the G by G max, at which particular value of cyclic shear strain you are using, that automatically is taken care of, that effect. Now, let us see what are the various effects of environmental factors and loading conditions on this damping ratio for normally consolidated as well as moderately over consolidated soil. If the confining pressure, effective confining pressure sigma m dash increases, in that case the damping ratio decreases with increase in the sigma m dash value, and effect decreases with increasing pi, that we have seen. With increase in the value of pi, the effect of sigma m dash on G by G max curve as well as damping ratio decreases. Now, what is the effect of void ratio? If the void ratio increases, the damping ratio decreases. What is the effect of geologic age? If geologic age of the soil increases, damping ratio decreases. What is the effect of cementation? With increase in cementation in the soil, the damping ratio may decrease with the cementation, but it is not so significant. So, effect of the cementation on the damping ratio is not very significant. The trend is minor decrease in the value of the damping ratio with increase in cementation. What is the effect of over consolidation ratio? It was observed by these researchers Dobry and Vucetich 1987 that OCR is hardly having any effect on the values of damping ratio. So, for different OCR values of soil, we can expect the damping ratio remains to be almost same. What is the effect of plasticity index? If plasticity index increases, damping ratio decreases, that we have seen just now in the plot also. What is the effect of cyclic strain? With increase in cyclic strain, damping ratio also increases. We have seen the curve, the pattern of the curve. And strain rate, the rate at which the strain is applied, cyclic shear strain, with that damping ratio remains constant or very insignificant amount of it can increase with the increase in the value of the cyclic shear strain rate with which it is applied. And with number of loading cycles, the change in damping ratio is not significant for a moderate value of the applied cyclic shear strain. So, these are the effects of environmental and loading conditions on the damping ratio value of normally consolidated and moderately over consolidated soils. Now, let us come to the relative qualitative assessment for various laboratory tests, what we have seen to determine the dynamic soil properties. It is given by Silver in 1981. This column gives the various names of the laboratory test, that is resonant column test, cyclic triaxial test, cyclic simple shear test, cyclic torsional shear test, and these are the parameters which we are obtaining: shear modulus, Young's modulus, material damping and effect of number of cycles. So, it has been observed that for resonant column test, we get a good estimation of shear modulus and Young's modulus and also a good estimation of the material damping, and effect of numbers of cycle is pretty well represented for resonant column. In cyclic triaxial test, the shear modulus means directly we are not measuring, we measured through it Young's modulus value. In material damping, it represent a good representation of the material damping, and effect of numbers of cycle is also good. In cyclic simple shear, shear modulus directly we are measuring, that is good, material damping is also good and number of cycles is good. In cyclic torsional shear also directly we can get the shear modulus and material damping, and number of effect of number of cycles is also good on the test. Now, various parameters which are measured during the cyclic or dynamic laboratory test in different test procedure are listed in this table. It is also given by Silver 1981, the summary of the different laboratory test like resonant column test, cyclic triaxial test, cyclic simple shear test, cyclic torsional shear test, and these are the parameters which are measured or not is mentioned in this way. So, load in resonant column test, we measured the resonant frequency. In cyclic triaxial test, we measured the cyclic axial load provided. In cyclic simple shear test, we measured the cyclic horizontal force applied, and in cyclic torsional shear test, we measured the cyclic torque applied to the system. Regarding the deformation, axial deformation, for resonant column test, we measured the vertical displacement. In cyclic triaxial test also we measure vertical displacement. In simple shear test also we measure vertical displacement, and as well as in torsional shear test also we measure vertical displacement. Regarding the shear, in resonant column test, it represented measured through acceleration. In cyclic triaxial, we do not measure shear. In cyclic simple shear test, of course, we can measure it through the measured value of horizontal displacement, and in torsional shear test, we measure it through the amount of torsion. Then coming to the lateral load, in resonant column test nothing is involved as such. In cyclic triaxial also nothing is involved. In cyclic simple shear test, the lateral load which is applied, often they are controlled lateral load, and in torsional shear test nothing is involved. Regarding the measurement of pore water pressure, in resonant column test, we do not have any chance or scope to measure the pore water pressure, whereas in all other three tests, that is in cyclic triaxial test, we can measure the pore water pressure at the boundary of the soil sample. In cyclic simple shear test also, we can measure the pore water pressure at the boundary, and for cyclic torsional shear test also, we can measure it at the boundary. And about volumetric strain, none are measured in all these tests for the undrained test, because when we are doing the undrained test, we are not concerned about this aspect. Now, let us see what are the various ranges of that cyclic shear strain amplitude, which are used for different dynamic test. So, ranges and their applications of dynamic laboratory test, these are this is the scale of shear strain amplitude. So, strain amplitude is here 1%, it is 0.5%, it is 0.1%, like that. In this direction it is decreasing. So, 10 to the power minus 4%, very small value of the cyclic shear strain. Now, what are the different types of test which are used for typical which ranges of the cyclic shear strain are mentioned here. Like when we said resonant column test with a solid specimen, then generally it is used in the test range for the shear strain in between about 5 into 10 to the power minus 3 to 10 to the power minus 4% of cyclic shear strain amplitude. That is the range which is applied to the soil sample while testing for a solid specimen. Whereas, if we use a hollow specimen in that same resonant column test, generally we can go little higher value of the cyclic shear strain amplitude, which is about 5 into 10 to the power minus 2% to about 10 to the power minus 3% of the value of the shear strain amplitude we can apply to our soil sample, and results we will get which are pretty good. And what we have seen, all the geophysical test using the travel time method, that is the basic concept, those are effective only at very small strain values. So, the shear strain amplitude ranging between about 5 into 10 to the power minus 4 to 10 to the power minus 4. So, these tests are good in this range only, means the values whatever we will observe from the test is good in this range of the shear strain. Whereas, the dynamic or cyclic triaxial, cyclic simple shear, cyclic torsional shear, these tests are good in the range of about 1% of shear strain to about 5 into 10 to the power minus 3% of shear strain amplitude. So, the application of the cyclic triaxial, cyclic simple shear and cyclic torsional shear is pretty wide. So, they cover at high strain level as well as moderately low strain level also. That is why when we had classified our laboratory test, we have classified them in small strain test and high strain test. So, small strain is basically this resonant column, travel time curve, these can be classified as the small strain testing procedure, whereas these tests of dynamic triaxial, simple shear, torsional shear, these are classified as high strain testing procedure. Another in this small range comes the piezoelectric bender element test, which also we have discussed. There also you are effectively measuring the travel time. So, that is again a small strain laboratory test. Now, what are their applications of these tests, or for what kind of dynamic load we should use? So, this is very important for a designer to understand that which test will be good for a particular design when they are taking care of under a particular type of dynamic load. So, it may not be universally true or generalized. So, this is very important. These are areas of applicability of the test results. See, the nuclear explosion or nuclear explosive, whatever strain, shear strain they will induce in the system or induce in the material of soil, they are of very high magnitude. So, the nuclear explosion problems related, or when you are dealing with design related to the nuclear safety related issues and loads are coming from nuclear explosion, in that case it must be in the high strain range. What does it mean? Which type of test we should use in that case? The results which we are getting from cyclic triaxial or cyclic simple shear or cyclic torsional shear, only those results are correct results to be used for design of nuclear structures subjected to nuclear explosive or a nuclear explosion type of dynamic load. If you use, suppose the value of G or value of damping ratio obtained from resonant column test for nuclear explosion, it will be again a disaster in your design, because in that case you have estimated value of G, which is a small strain value of G, is not at all applicable for the range of shear in which the soil and the structure is subjected to during the dynamic load of nuclear explosion. So, be very careful about the selection of type of test as per the areas of application. Now, coming to the next type of dynamic load which we commonly use as a designer, the structures or soil which are subjected to ground shaking or earthquake loading. So, for earthquake loading, the typical range is given here, about 5 into 10 to the power minus 2 to about 5 into 10 to the power minus 3% of shear strain, that is a typical range I am telling. So, for that strong ground earthquake motion, when you are using the laboratory test results, dynamic shear modulus and dynamic damping ratio value, in that case again it should come from either dynamic or cyclic triaxial test or simple shear or torsional shear value, or maybe at most resonant column if you have used hollow specimen. But resonant column of solid specimen, if that value if you use for earthquake analysis, again it will be giving a wrong design procedure. Your input value will be wrong, then obviously your further calculations will be not correct. As well as if you use the piezoelectric Bender element values or any travel time values which where you have computed the value of Vs, which is the case for SASW test also, which you estimate the Gmax only. So, using that for earthquake analysis most of the time it is questionable. So, you should not only have an estimate through a field test of Gmax through Vs value, but also you should do a cyclic test for your sample at laboratory. Better to use the triaxial or simple shear or torsional shear with cyclic loading. Whereas, if you handle the problems related to machine design, in machine design problem your machine foundation and corresponding soil mass, they are subjected to very low value of shear strain amplitude compared to the other two cases, in this range of 10 to the power minus 4 to 5 into 10 to the power minus 4% of shear strain typically. Why? Because in case of machine foundation, we do not want the foundation or the entire assembly to move by or to displace by a large amount. So, displacement or displacement amplitude is always restricted to a very small amount. That is the reason why your machine foundation is subjected to very low value of the shear strain. So, for machine foundation design, which are the good test, laboratory test you can use? Resonant column test, travel time test, bender element test, piezoelectric bender element test, all these values of dynamic soil properties of G and damping ratio you can effectively use for the design of machine foundation. So, only for design of machine foundation this test will be proper. Again, this test when you are using from the cyclic triaxial, cyclic simple shear, you have to use a very high value of G max at the initial stage. So, application of cyclic triaxial, cyclic simple shear and cyclic torsional shear is not that so good for machine foundation, but can also be used, because it is always you are estimating on the lower end. Okay. As a designer, this is most important observation one should have. What are the typical ranges of shear strain amplitude for different laboratory tests to determine dynamic soil properties? Based on that, we know for different types of applications which test should be suitable for us to apply. Coming to another type of test, which is pretty commonly used in static case also, plate load test. In this case, to determine the dynamic soil property, we will use cyclic plate load test. So, in cyclic plate load test, what are the procedure? Let us note it. The force per unit area acting on the plate is nothing but total load applied on the plate, say capital Q, by area of the plate. Generally, square type of plate are used for plate load test. You are aware of the static plate load test. So, the same thing is used in case of cyclic plate load test, only changes instead of a static loading, we will apply load in cycles, we will see that. So, what are the steps? We need to calculate the elastic settlement by applying cyclic load on that plate. So, these are the elastic settlements. In the next figure, we will show what these elastic settlements are. Plot a graph of that Q versus the elastic settlement and calculate the spring constant of the plate using this expression. The spring constant of the plate is nothing but this force per unit area, which we have measured from this plot, times the area of the plate divided by the average elastic settlement. I will show that what we are doing in the plate load test. So, through a static plate load test, you are aware of, we can draw the distribution of load per unit area, that is small q versus the settlement. That is, for any plate load test, we can easily draw load settlement curve. This is nothing but load settlement curve. In your x axis, you can draw load per unit area also, or the load itself also, versus the settlement. In cyclic plate load test, what we are doing? We are starting from here, graph is coming, this is the loading curve. Then we remove the load completely, take out the full load. So, as the soil is not fully elastic, it will not trace back the same path, it will go in some other path like this. Then you again apply a higher value of load to the plate. So, the curve will come here. Then in the next cycle, you take out that load also completely. So, allow the load to come to 0. So, that is the point, always take out the load fully, do not keep the load partially, take out the load fully. Then in the third cycle, again you apply a higher value of load, then take it out fully. Then again in the next cycle, you apply a higher value of load, take it out fully. So, what does it mean? When we are applying a load here and then taking out the load completely, whatever the settlement it remains, that is the settlement with the load applied, say small q1 was this much, and after taking out the load, the soil has come back to this settlement. What does it mean? This amount of settlement is nothing but the plastic settlement, which the soil material could not regain, whereas the amount of settlement which the soil material could regain is this amount, this difference. So, from here you draw a parallel line intersecting the settlement axis, and this value you know. So, the difference between them is nothing but the elastic settlement component for the applied load of Q 1. Similarly, in the next cycle what is happening? When you are applying load Q 2, the total settlement is this much up to this. So, draw a horizontal line from there. Next, after taking out the load completely, the settlement remains up to this. So, the amount of settlement it could recover is this much value. So, this is the elastic settlement under the load Q 2. So, this is S E 2. So, this is S E 1 corresponding to load Q 1, S E 2 is the elastic settlement corresponding to load Q 2. Similarly, in the third cycle, this is the full settlement. After taking out the load, the remaining settlement is up to this. So, elastic settlement is this much, S E 3 is the elastic settlement corresponding to load applied Q 3. In the fourth cycle, for the load applied Q 4, the total settlement is this much, and after taking out the load completely, the settlement remains up to this. So, this much is elastic settlement. So, S E 4 is the elastic settlement for the applied load Q 4. So, we got the estimation from this load settlement curve from the cyclic plate load test, that what are the values of corresponding elastic settlement to this applied load. So, what we are doing next? Next we are drawing another plot with this y axis as load per unit area, that is small q, and this x axis as elastic rebound or elastic regain or elastic settlement, which we have just now estimated from the original load settlement curve of the plate load test. So, this is S E 1 corresponding to Q 1, S E 2 corresponding to Q 2, S E 3 corresponding to Q 3 and S E 4 corresponding to Q 4. So, these are the different numbers of points. So, as you use different cycles of loading, you can get several numbers of points, and obviously, for a particular test it is desired that you use at least more than 3 numbers of test points you should get. So, from that now you should do, or you should draw an average line of this Q versus elastic settlement. As this is a elastic settlement, obviously the relationship must be a linear relationship through the origin. So, you draw an average line through these test points which passes through origin and which can represent these all your test points very effectively. So, the slope of this curve is nothing but what is mentioned as that stiffness. Let us see that. So, let me go back once again in the calculation. So, the spring constant of the plate is estimated like this. K of plate is given by that Q by S E is nothing but the slope of that curve times the area will give the spring constant. So, in this way the stiffness of the plate material is obtained. Now, we need to convert this stiffness of the plate to the actual footing or actual foundation which we are going to use. The same thing what we have done for the static load test, here also for cyclic load test we need to apply. So, let us see what way we can compute the stiffness of our footing, because for any design we should know what is the stiffness of our footing material. So, the spring constant for vertical loading for a proposed foundation can be extrapolated from the plate load test as proposed by Terzaghi in 1955. For cohesive type of soil, the stiffness of the foundation or spring constant of the foundation is given by K of plate times foundation width by plate width. Whereas, for cohesionless soil, it is given by the stiffness of the foundation is nothing but stiffness of the plate times foundation width plus plate width divided by 2 times plate width whole square. So, in this manner we can find out easily what is the stiffness of our foundation to be designed, and then using this value we can further do our dynamic analysis, because in all our dynamic analysis we need this value of spring constant, that is one of the basic input we require. So, this is the way, in a simplified manner, we can compute the stiffness of the foundation. Now, how to compute the shear modulus from this cyclic plate load test? It can be shown theoretically as proposed by Barkan in 1962, that Cz is defined as subgrade modulus, similar to our static case of soil subgrade modulus. What is subgrade modulus? The unit of subgrade modulus is nothing but pressure per unit displacement, right. So, in this case, from the cyclic plate load test, the subgrade modulus, dynamic subgrade modulus, what we are computing is nothing but that slope of the curve q by SE. So, what does it mean? Let me go back to the picture once again. The slope of this curve is nothing but the dynamic subgrade modulus, and what will be the unit of that? If q is in kilonewton per meter square and this settlement is in meter unit, that is all SI units if you use, the unit of the subgrade dynamic subgrade modulus will be kilonewton per meter cube. And what is the unit for the K of plate? That should be kilonewton per meter. So, this is kilonewton per meter cube times meter square, the plate area, you are getting kilonewton per meter. And for foundation, K of foundation also it should remain the same, kilonewton per meter in SI unit. So, dynamic subgrade modulus is computed from the slope of the curve, which is represented by this expression 1.13 times E by 1 minus mu square times 1 by root over of A, where this E is nothing but Young's modulus, mu is Poisson's ratio and A is the area of the plate. So, as kindly note that this expression is valid for only vertical vibration. So, please note it down, it is valid only for vertical vibration. For other modes of vibration, that is horizontal, rocking, pitching, etc., we will see other expressions available to compute or to correlate between the dynamic shear modulus with the Young's modulus. So, this expression is truly speaking valid for vertical loading only or vertical vibration only, as it is mentioned in the previous slide also, that this is also valid for only vertical loading. So, using the cyclic plate load test, we have already obtained Cz. In this case, Poisson's ratio of the soil, if it is known, area of the foundation or area of the plate, whatever you are calculating, correspondingly you can get the value of the E, modulus of elasticity. How you can use it to obtain the value of G of the soil? This is the expression or relation between G and E, as we know from the basics of the Lami's constant. This is the expression or relation between shear modulus and Young's modulus, that we can use in this expression of Cz, which on simplification will give us, this is the expression to compute the value of G. So, the magnitude of dynamic subgrade modulus Cz can be obtained from the plot of this Q versus elastic settlement with known value of area and a representative value of the mu for the soil. The shear modulus can be calculated from this equation. Okay. So, this is another way to calculate the dynamic shear modulus. So, with this we have come to the end of this lecture. We will continue our lecture in the next class.